Okay, so welcome everyone. I would like to look today into the problem of estimating the parameters of a camera. This can be the intrinsic parameters and can also be the extrinsic parameters. And we'll basically propose or present you two methods. The first one is a direct linear transform, which is a technique given a few known control points in the environment, so points in the 3D world about which I know their 3D location, how I can actually estimate where the camera is and what the parameters of this camera is. So the intrinsic parameters like the camera constant or the principal point and different aspects like that. The second technique, Zhang's method, is a different technique. That one doesn't use a natural scene about which we know some known control point, but it uses a special pattern. So basically a 2D, what's called a checkerboard pattern, so like a chessboard with black and white pixels, and you can actually hold this pattern in front of your camera, and by exploiting the knowledge about this checkerboard, we can actually estimate the intrinsic parameters of the camera in this way, calibrate our camera before we go in the field, do measurements, and then do not require special control points during operation. So what's the idea? Consider we have images of a scene and we know something, let's say the location of those red crosses over here. There's something which you can call control points, so points about which we know their 3D location in the world. And the question is, if I have such an image, can I actually tell something about the parameters of the camera? So based on these images, if I know the location of those images, can I actually tell from which location this image has been taken? And can I also say something about the camera constant or other intrinsic parameters of the camera which was used to take that picture. And this is exactly what we are addressing. So given some known geometry about the scene, can we actually estimate the parameters of the camera, intrinsic as well as extrinsic parameters? So this is, in this case, a single image. This is just two buildings nearby which look similar, but the scene looks in reality like that. So what are things we can do if we have such a technique at hand in order to estimate the parameters of a camera, so intrinsics as well as extrinsics? So several things are possible. The first thing I may be interested in is just calibrating my camera. So I have a camera I don't know anything about, and I actually want to estimate the intrinsic parameters. That's one of the topics that we are actually looking into today. The second thing what I might get interested in, I want to estimate the position in terms of X, Y, Z position and the three angles for the heading from where an image has been taken. So if I know something about a building and I take an image from that building, can I actually estimate where this image has been taken from? Or the other way around, if I know where a camera is in the scene, can I actually use that to estimate the 3D location of objects in the scene. So these are all relevant problems that we are addressing, and we are looking today into camera calibration and estimating at the same time the extrinsic parameters given some information about the 3D scene. And we do that again in two different ways. One, if we have control points, that means we have some point in the environment about which we know their X, Y, Z location. And the second technique is something where I'm not necessarily interested in knowing certain things in the environment. I take a 2D pattern, like this checkerboard with black and white areas, and hold that in front of the camera, take multiple images of this checkerboard, and then can use this to estimate the intrinsic parameters. In this case, I'm typically not interested in estimating the extrinsic parameters, although I may need that during the process, but the result are the intrinsic parameters of the camera and not the location of the camera. So we start with the first task, which will lead us to the so-called DLT, or direct linear transform. What we want to compute is the extrinsic and intrinsics of my camera. So where the camera in the world, and what are the 5 parameters for the of the intrinsics. And what I assume to have been given is coordinates of objects. So I know the 3D location, the 3D coordinates of certain points or certain objects in the scene. And these are my control points. This is given. I need to know this as background information in order to do this process. And what I observe or what I measure are the XY locations of the pixel in my image that correspond to the objects for which I know their 3D coordinate. So basically take pictures of a known object, and then I want to use this information of where this to which pixel the objects have been mapped to in order to estimate the parameters of my camera. So the word direct linear transform is once used for this mapping process that we discussed last week, but it's also used for estimating the parameters of this process. So again, we have our camera, we have the kind of the reference system of the camera, so where the camera is with respect to my world reference system. Also, I know where they're heading for. We have our image plane, and we have an object, and I know the 3D location of the point. And by measuring where this point is mapped to in my image, I can actually estimate where I can estimate the parameters of that mapping in order to make sure this point is actually mapped to this pixel location. So this was the mapping. We have the point in my image. It depends on the calibration matrix, which is an upper triangular matrix for the fine camera. It has 5 degrees of freedom. So on the main diagonal, we have the focal length and the kind of difference in the scale for the x and y coordinate. We have the shear, and we have our principal point. Then we have a rotation matrix, which describes where the camera is actually looking to. And we have the location of the pinhole in my pinhole model in the 3D world. And then any object point x is actually mapped to this image point. And if I combine this into one matrix, it's typically described as a matrix P and a 3x4 matrix. So this is a 3x3 matrix. This is a 3x3 vector. So this describes here a 3x4 matrix. And this matrix realizes a projection from the 3D world to my camera image. Okay, so that's a task that I want to do. And this matrix P now encodes all the extrinsic and the intrinsic parameters. So these are encodes the intrinsics, and the R and the X0 are the extrinsic parameters. And I want to estimate that at the same time, the intrinsics and the extrinsics, from known correspondences. So knowing the 3D location of the object in the scene and knowing where the point is mapped to. And this is all in homogeneous coordinates, therefore it's a 3x1 and a 4x1, although this is in the 3-dimensional world and this is in the 2-dimensional world. So it's the task is to estimate the interior orientation of the intrinsics and the extrinsics. That means X0 and R and the calibration matrix K. So there are kind of 2 different ways to do that. We will look today start with something which is called the direct linear transform. In this case, I only observe where an object is mapped to, and I know the coordinates of my control points. I assume this to be given. So this is given. This is what I measure. What I estimate are the red elements. So 3 degrees of freedom for the rotation matrix, 3 degrees of freedom for the translation, and 5 degrees of freedom for my calibration matrix. So that's a task that we will address in the first hour today, based on known points. In the second part of the course today, we will replace this with our checkerboard, and then a few things will change in here. We can simplify a few terms and then do this for the checkerboard. There's a second task that is pretty important, which is called spatial resection or projective 3-point algorithm, are 2 names for exactly the same thing, or räumlicher Rückwärtsschnitt in German. And what we are trying to do here is we only want to estimate the extrinsics, so where the camera is and where it's looking to, given we know K. And that's something which will happen on next Tuesday, so day in a week. So this is just kind of an outlook. If we know the intrinsics, our problem gets easier. We only need to estimate the extrinsic parameter. That's something we are not going to do today. It's just an outlook of what will happen next week. We address today this problem, but we want to estimate all the parameters at the same point. Obviously, we need more observations if we try to solve this task, so we need to have more, we need to know more control points and need to observe those points in our images. And we need less for the projective 3-point algorithm, but that's something which will actually happen next week. Okay, so the first thing we may ask ourselves, how many points, how many control points do we need to know? So each of those points gives us how many observations? Why? So these points here are given. So let's expand that. So those points, so this is just a normalization concept. This is a 3 coordinates, that's true. But those are given. So those we have. And those are the guys we're actually observing.
It's only 2 because then we don't know how far away.
Yeah, so we only can measure the pixels in our image or the location on our sensor. So we only get kind of 2 of them. So again, if we normalize this, you see this is 1 and this is 3 parameters, these are 2 parameters. And you can perfectly see these relations if you write down the pixels, the mapping from the 3D world to the pixel coordinates in our image in Euclidean coordinates. So we have all those elements of the projection matrix, the x, y point in the 3D world, and that's what we measure. This is what our model tells us. So we basically get 2 equations for every point that we have. Okay, so if we have a calibrated camera, that means we have 6 unknown parameters. 3 for the translation and 3 for the rotation. That means we need at least 3 points that we need to observe in order to estimate where the camera is. So at least 3 points, the 3D location of 3 points in the environment we need in order to estimate the extrinsics of a calibrated camera, given we know the calibration. And this is something which will happen next week. We'll be looking today into the problem of the uncalibrated camera. That means we do not know the calibration matrix. The calibration matrix has 5 additional degrees of freedom. That means we have 11 unknown parameters over here. In order to estimate those 11 unknowns, we need to have at least 6 points now in order to estimate those unknown parameters. Of course, we again have our mapping where we get 2 observation equations for each point, and if we have 11 unknowns, we need to have at least 6 points in order to do the estimation. And that's something which we are going to solve with the so-called direct linear transform, and this is exactly the task that I want to address now. Okay, again, estimate the 11 elements of P. So P has only 11 degrees of freedom because it's homogeneous, so 1 is for the normalization, although there's 12 elements. Well, we have the 3D location x with index I of at least 6 points, and we have the observations where this point is actually mapped to in our image. Okay, so the first thing we do is we say, okay, let's simply write down what this matrix actually means. So we can actually write this down as the 3x4 matrix with our 12 elements of our matrix. The first thing we do, we just rearrange or just rewrite those equations by saying, okay, let's define a new vector A, which corresponds to this row over here, a vector B, which corresponds to this row, and a vector C, which corresponds to this row. If you do this, we can simply write the same thing as A transpose, B transpose, C transpose, where these are the individual vectors. So this vector A is P11, P12, P13, P14. So we transpose it, so it becomes here row, and so the colors indicate the corresponding things. And this is just a definition how we define it. Nothing has happened except of rewriting this in this form. If we use this way of writing that, then we can actually specify that this point in homogeneous coordinates, so ui, vi, wi, can be expressed by multiplying this vector with this vector. Over here, it corresponds to u. The vector b transposed by xi gives me the second coordinate, and c times xi gives me the third coordinate. Okay? So no black magic has happened. We just kind of introduced some auxiliary variables a, b, and c in order to simplify our life. Oops, okay. That should actually come like this. So this is just copy-paste what we have written on the previous slide. So this part was copy-paste. And we know that this corresponds to xi, yi normalized. We want to normalize this, because this means we take ui divided by wi and vi divided by wi. So I can say xi is ui divided by wi is x transposed xi, this line, divided by the third coordinate. And I can do exactly the same thing for the second dimension. Well, the only thing, what we did so far, we looked into what happens if you do the multiplication of the projection matrix and our point in the 3D world. We introduced these auxiliary variables, a, b, and c, and then we can express the x coordinate and the y coordinate, where we expect this point to end up on our image plane, on our chip, in this way. Okay? Okay, so just put them here, and then we can do a slight rearrangement. We can multiply by this expression. So this one goes over here. We can subtract the remaining expressions, also goes over here and equals to 0. So we have x times c transposed xi minus a transposed xi equals 0. And you can do exactly the same thing for our y coordinate. Take our y coordinate, b transposed xi divided by c transposed xi, and rewrite it exactly in this way. Okay, remember, those x were the points that we know. So these are the coordinates of our control points. What we are interested in is estimating this projection matrix P, which consists of A, B, and C. So what we now have is here equations, and those equations are actually linear in A, B, and C. So I can slightly arrange those things by basically performing the transposition, and then it's minus x transposed A plus xi x transposed C, and the same thing down here just with B. So I have my unknown parameters A, B, and C, and a system of equations which is linear in the parameters A, B, and C. Okay, so that looks good. Something that we actually can plan to exploit. So what we want to do now is estimate not only A, B, and C all at the same time. So we can again slightly rewrite that by saying we introduce a vector P, which is just A, B, and C stacked on top of each other, which is simply the vector of all elements in the projection matrix. So it's P11, P12, P13, P14, P21, P22, and so on and so forth, all stacked up with the vector. So this is in this case 12 by 1 vector, because P has 12 elements. So these are the rows as column vectors, one below the other, so it's a 12 by 1 vector over here. And that means we can actually rewrite our system of linear equations that we have here in a special way, with two equations with some magic vector A transposed times P, so P contains all the elements in A, B, and C, and a second vector A for the y coordinate times the same matrix P equals 0. And we get that if we define this vector A, B, and C in this way. So this may sound a little bit counterintuitive, or actually, why do I actually set up something like this? I hope this will become clear, because it will simplify the math that we are going to do substantially. But the first thing is I kind of provide you this two vectors A, and I claim that this equation is exactly the same equation over here. If I just claim that, we should actually verify that this is correct. So let's simply give it a try and perform this computations and see if we actually end up with the same system of equations. Okay, so let's verify that. So this was my AXPI, just the x, y, z coordinate, or the negative x, y, z coordinates of the point in the 3D world, and a 1, then a couple of 4 zeros, and then the product of the point in the image coordinate system and the vector, the coordinates of the vector of the point in the 3D world. And I multiply this is just all 12 elements of my projection matrix. We just need to check if this equals 0, this gives me the same constraints as this system of linear equations. So again, this corresponds to A, this corresponds to B, this corresponds to C. So I can actually rewrite this vector as, again, ABC. And those guys over here is this point xi transposed. This is a 0 vector for D, and this is my point x times x transpose. So the x coordinate of the observed points times the coordinate of the coordinates of the object point in the 3D world. What I then can do is, if I multiply this vector with this vector, I get minus xi transposed A. Second element is 0, so no dependency on B. And then x. Okay, I forgot to remove the prime. This is a mistake. I tried to unify the notation. I forgot to remove this prime. So this is exactly the same variable. So this prime should go away. And so this equation is exactly the same equation that we had over here. And this is, if we go back on our slide, exactly the first line over here. So this, performing this multiplication leads us exactly to this line over here. Okay, and we can do now exactly the same thing in exactly the same way for y. Then we don't have the coordinates of the point here as we had it before for x. It just moves over here, and we have the y coordinates over here. That's how we define the vector a, y, and the rest happens completely in the same way. And we get the same system of linear equations. Again, the prime here should be eliminated. So what we have shown so far is that the system of linear equation that we derived is exactly the same as those two constraints over here. Okay? Everyone happy up to that point? We have done nothing very fancy. We just rewrote our equations by defining some new vectors and then showed that the product of this vector A and the vectorized matrix is exactly the same condition as which resulted from our system of linear equation. So what we do now, we have that done for one point xi, and we can do that for all points. So we said we need at least 6 points, so we need to do that for at least 6 points. So every point has the same matrix over here. Of course, they're all taken from the same image, so they have the same matrix P. We just have different coordinates over here, where the point is in reality and where we observed the point in the image. So we simply do that for at least 6 points, or for I points, at least 6. And then we can actually, again, stack them all up in form of a matrix over here and multiply this with this matrix P. So we have here a 2i times 12 matrix and a 12 by 1 vector. We say this product should actually be 0. Okay, if you take real observations from the real world, the thing will not be 0, as you all know. So we will get some contradictions. If we multiply m with p, we will have some contradictions. And it won't be 0. So what we are trying to do, this should be obvious to you, we take w transposed times w. We actually want to minimize that. So we want to estimate the projection matrix which minimizes the sum of the squared errors. So that's our goal. Find the projection matrix that minimizes the squared error that, that results from those constraints over here. And minimizing this means minimizing this, just replacing the definition in here, and then we have, yeah, that's true, that's correct. The only thing we need to take care about this matrix P is this matrix P is a homogeneous matrix. What does it mean to have a homogeneous matrix? inhomogeneous coordinates, a matrix M and a scaled version of the matrix M are exactly the same. So I have a scaling parameter in here. And this P are the elements of my matrix, what I'm basically looking for. So this actually shouldn't be written with M, but of course it's arbitrary, but I actually want to say P equals lambda P. So because we're talking about the projection matrix. So my vector P here can be arbitrarily scaled. That's really nothing I want if I want to minimize an error. So I add the additional constraint that kind of we fix the normalization. And this is by requiring that the norm equals to 1. This is one way for kind of fixing the scale. So what we do is we have to solve a least squares problem where we need to make sure that we have this problem that's actually basically what I was told before is least squares problem, but it's so-called algebraic minimization. So there's no direct geometric relation to what I see in terms of the errors and pixels that I have because we have this scaling in there. We need to fix this scale parameter at some point. Okay, so how do we solve the system of linear equations to actually minimize the squared error? But for that, we can treat that as an eigenvector and eigenvalue problem and then use SVD in order to solve that. Something you should have seen before. Nevertheless, I would like to go through these individual steps so that you see the direct correspondences, how we can use SVD in order to solve this problem, because that's something that we will actually need in the remainder of the course or in the beginning of the Photogrammetry II course. We will use exactly the same technique in the same way for estimating different matrices when we look into stereo images and the orientation of stereo cameras. Okay, so that's what we want to have. What we can do is we can compute the SVD of this matrix M. What was the SVD? So we have two matrices over here, and UU transpose as well as VV transpose are identity matrices. So you can see this as a rotation. And we have this matrix S, which is a 12 by 12 matrix, which is 0 everywhere except the elements on the main diagonal. These are the singular values. And this can be arranged in a way that the singular values, S1 is the largest one, and S12 is the smallest one. So it's just computing the SVD of this matrix M. This SVD decomposes this matrix into three matrices. And now we'll actually exploit that SVD, so this decomposition, in order to show how we actually should select this matrix P so that it minimizes the expression over here. Okay, so this was our linear system that we wanted to solve, but of course we will have contradictions in there. This will be non-zero. So what we're actually doing, we are minimizing the contradictions. And we're using this, the SVD, so this decomposition, in order to solve that problem. If we apply the SVD, we start with this expression over here and simply replace the W's by M times P, and then we'll actually see that we can use the SVD directly to actually find the solution. This happens as follows. So the sum of the squared errors is W transpose W. So I can say W equals M times P, so this is P transposed, M transposed, MP. Just the definition of our contradictions. Then I use the SVD and decompose the matrix M as well as M transposed, which gives me V as U, this is the SVD of this matrix, times U as V transposed, this matrix P. And now we had the effect that we said UU transposed was the identity matrix. So this goes away. So what I have is P, I'm missing a transposed here. So there should be a transposed. It's back here on track. So U goes away, I have F squared, which is just the matrix, because there's only elements on the main diagonal where I just have the singular values on the diagonal squared. So I can express this as my vector P, the product of the 12 diagonal elements, this is Si squared, and then this vector V. Okay? So what I just did so far is, using the definition of the squared errors, using the SVD, applying the SVD to the matrix M, do some trivial replacements by just saying U transpose U is the identity matrix, and then squaring the elements on the main diagonal, and then I actually end up with this equation. Okay, so this was just copy-paste from the previous slide. Now I know that those SVDs, that the vectors in this V are all orthogonal. So VI transpose is 0 if they are identical, is 1 if they're not identical. So if we now choose, so they are, as we are going over the main diagonal, this is 1 all the time. So the remaining part, the part which remains is if we set our vector P to the 12th element, then then all will be 0 except the last one. And so the squared error turns into the corresponding singular value squared. So just by choosing P as a vector which corresponds to the smallest singular value, this sum simplifies in a way that only the smallest singular value remains. So it's the smallest one of all of them. So the squared error reduces to the square of the singular value. So by choosing P as the eigenvector corresponding to the smallest singular value, SIV, we minimize the squared error. So what we basically in the end need to do in order to perform this minimization, we just compute the SVD on this matrix M and choose from this matrix V the vector corresponding to the smallest singular value, and this is then the solution to our matrix P, or to our vector P, which then turns into the matrix P. This way, for using this, the SVD in order to solve this system of linear equations, or to minimize the squared error that corresponds to the system of linear equations that minimizes the contradictions for that system. You can do that. I do not need to iterate here. You can do that in one shot. Okay, so in this way we have our estimate of P, which is V12. This corresponds to my estimates of A, B, and C. So we directly get the matrix as the estimated elements are the elements here of my vector A, B, and C. Right? So what I have done now, I have computed this projection matrix. What do I need to take into account if I want to do that? So this matrix M is of rank 11. Because my 11 unknown parameters. In order to have that, I need to have at least number of points which is larger than 6, and I don't have any gross measurement errors in there. So I only have my noise in there. If I have measurement noise in there, I may be off. But I also need to take into account that there are some constellations in which I can't compute a solution. And one of the critical points for the DLT, especially in aerial photography, is if I have non-control points on the ground and I want to use those non-control points on the ground in order to estimate the parameters of my camera, and they are all lying on one plane. All the control points on the ground lie on one plane, then I actually can't find a solution. And we can actually show that. So I have all my elements in here. This corresponds to this matrix where those are those large 12-dimensional vectors as we defined them before. And if I now assume that they all lie on a plane, for example, z equals 0. Take any plane, but you can directly see that if z is equal to 0. So they're all on a ground plane or on a plane. Then all those elements here will turn into zeros. And this holds for all points, so this holds for all elements of the matrix. All those columns will turn into zeros. And then I have a reduced rank and can't find a solution. So the important thing for the DLT is that not all points are supposed to lie on one plane. So even if you take a different plane, not the z equals 0 plane, you can actually observe the same effect, but here you can nicely see that those vectors, or those vectors over here within this matrix turn out to be 0, and they can directly see that it has a reduced rank. But it holds for if those points lie on a plane. There are actually more complex configurations. If they like on a twisted cubic curve, all the points and the projection center, but this is something you can't see that easily. And this is something which rarely happens in reality. But that the points should not be located in a plane is something that you can see, which happens in real-world problems. So if you fly with an airplane, for example, taking aerial images, and you want to estimate the parameters of your camera and where the image has been taken from 6 non-control points on the ground, then those 6 control points are not supposed to lie on the plane. And even if you're very near a plane, you get an unstable solution. Okay, what we have now, we have P. We have P, but what I actually wanted to have was K, R, and X0, right? We wanted to know what are the intrinsics of our camera, where is the camera looking to, and where is the pinhole in the 3D world. So what we need to do now is we need to decompose P to estimate those matrices. To know what, for example, the camera constant for our camera is. Okay, how are we going to do that? Let's look to how our projection matrix looks like. So P is known, but not the individual elements. So it must be K multiplied with R, multiplied with this matrix. We have the identity matrix over here, 3 by 3, and then the translations over here. And we can actually write this P as some homography 3 by 3 matrix H. Just ignore the 0, though we don't need that 0 here for the moment. And a vector, a 3 by 1 vector. Okay? So then this element over here corresponds to K times R times the identity. This gives me H for this equation over here. And this H is minus K times R X0. The head is missing here. Sorry. Okay? So the first thing is, how do we obtain the projection center? That is pretty easy, because K times R are exactly those elements of the matrix. So these are the 9 elements I can just pick from my matrix P. Just picking those 9 elements of our matrix P, I can use this in order to compute the projection center, just by saying, okay, X0 is simply minus this matrix H inverted times H. So I basically take my projection matrix on which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3 elements. Those over here directly form H infinity, and this was my vector H. So the only thing I need to, I pick this out, I invert it, which gives me H to the power of minus 1 at infinity, and I have my vector head over here, H. And then I can use those two, to compute the projection center. So that's something I can obtain easily from my projection matrix. Is that clear? Okay. Yeah. Please. So I only obtain a solution for P if the points don't lie on a plane. So I assume they don't lie on a plane, which I can actually easily check, and assume to have computed a solution where this holds.
And then this block is always invertible?
This block is invertible, yes. You can see that from the fact that, also if you know what it means, what those elements are, This is a rotation matrix, which is always invertible, and it's the camera calibration matrix, which has on the main diagonal the camera constant, which is not 0. Otherwise, the projection, everything would be projected into the same point. So the image would consist of just one single pixel in 0, 0, 0. And then we have all other elements are just the translation of the system, which is invertible, and we have the shear and the kind of the shift in the camera constant. So these all form an upper triangular matrix. Those elements can't be 0 in the diagonal, so I have an invertible matrix. Okay, so that was easy. This can be a little bit more difficult. So what I now want to do is I want to actually decompose a matrix H into two matrices. So I have an invertible matrix, and I want to decompose in two matrices, where one is an upper triangular matrix, and the other one is a rotation matrix. I guess you should have heard a technique which does exactly that. Two famous ways for decomposing a matrix, and one of them is the one to pick. So what are the two key ways for decomposing a matrix? Cholesky is one which I don't want to use here, because you have a lower triangular matrix. So one is an upper triangular matrix. QR decomposition, QR-Zerlegung, which basically decomposes. So if you have an arbitrary matrix, whatever A, and this is whatever compose the matrix M and D in this example, then this is a rotation matrix, and this is a triangular matrix. So this is what I have: rotation matrix, triangular matrix. My matrix H, however, is the other way around. K and R. So we would actually have to have that swapped. What I can do in order to fix this, I just take the inverse of H. First, the inverse is the inverse of those matrices, which is the inverse of those elements, the individual elements swapped. And for the rotation matrix, it's simply a transposed matrix, and then k to the power of -1. And then I exactly end up in this form of having a rotation matrix and my triangular matrix. And K is a triangular matrix. That should be clear. Of course, all the elements at the bottom, in the lower triangle, are 0. So just by using this trick, of using the QR decomposition and of using the inverse, I can actually break that down and this way compute R and compute K. So what I finally need to do, due to the homogeneity of K, again, need to do a normalization, which I can just by dividing it through the third element, so the ninth element of my matrix. And this gives me my calibration matrix. So this is just based on the QR decomposition of a matrix, that it decomposes the matrix into a rotation matrix and into a triangular matrix. And I can exploit that to get this decomposition into a rotation matrix and my calibration matrix. The only thing, if I do that, we said there are two, if you remember the lecture last week, there are two ways for defining the coordinate system of the image plane for a camera. One was with a positive camera constant, and one was with a negative camera constant, if you remember that correctly, or if you remember that at all. So we said we want to use a negative camera constant. But this approach has no idea if my camera constant should be positive or negative. So basically don't know what I get. However, the nice thing is we can actually easily fix this by introducing an additional rotation matrix, which just does the rotation by 180 degrees. So what I simply can do is, If my camera, with the decomposition ends in a positive matrix C, I can simply add a different rotation matrix and rotate it by 180 degrees, which is just this matrix over here. And I multiply K as well as R with this matrix, and then obtain the same result. It's kind of identical of flipping the camera and moving the image plane to the other side. It's just kind of two possible ways how this projection can work. And I need to define the coordinate system and then do this transformation the same way. Otherwise, the camera would look into the wrong direction. But I mean, the projection, these projection equations do not know something about the field of view of that camera. They just look into where the point projected to, given my the pinhole of my camera and where the image plane lies. So if I flip it to the other side, it could also flip the camera. This is just the thing we need to take into account here. Okay, so this was a DLT. So let's summarize DLT in a nutshell. So if you want to apply that, what you need to know your 6 points in the world which should not lie on a plane. And you need to know those coordinates. So the first thing you do, you start with your matrix P, which you don't know, which you want to estimate, and you need to vectorize that. The next thing you need to do, you need to build your SLE system of linear equations, a linear system of this matrix using these vectors A, which consists of the x, y, z coordinates of every point, and where the x and y coordinates of this point is mapped to into the image plane. To set that up, and this gives you your matrix PM, for which this should hold. Once you build up your matrix M, you apply the singular value decomposition on this matrix M. So, okay, you compute the SVD, which gives you those elements, and then you look into the matrix V, take the eigenvector which corresponds to the smallest singular value, and this specifies all those elements of your projection matrix. There's actually something, yeah, should be swapped, but doesn't matter. So the elements in this matrix V correspond to those elements in your projection matrix. Third step done, you have your projection matrix. If you need more, so if you want to know what is my camera constant, what's my principal point, what is the orientation of the camera, you need to decompose this matrix P using this one first and then the QR decomposition. So what you then do is, if the individual parameters are needed, you need to invert the matrix H infinity, so this part, so this block over here, you can directly compute the location of the pinhole, and with the QR decomposition you can directly estimate the rotation matrix as well as the camera, the calibration matrix. And this then encodes all the intrinsic parameters of your camera. So kind of to summarize to discuss this, what we now have, we have a mapping from P to my camera constant, my rotation matrix, and my projection centers in both ways. So if I have those three elements, I can trivially compute P, and even if I know P, we now have a way to do this computation. So we have direct mapping in both ways from P to the individual parameters and the other way around. We are free to choose a sign of my camera constant, so we can define our coordinate system in the way we want it, if it's the image plane is in front or behind the pinhole. We're completely fine. We know how to do that just by introducing this additional rotation. The points are not supposed to lie on a plane, and even if they're very close to a plane, may get an unstable solution. And what also should be clear is that the solution is not statistically the optimal solution. So it's a pretty good initial guess, but it's not statistically optimal. Why? Because I don't take into account the uncertainties of my image point, how I measure them in the image, and the uncertainty of the points in the 3D world. I can take that into account, then I can't apply the SVD in the form which was used in here. Then you need to do a standard Gauss-Markov model and derive those parameters. So kind of to summarize the key things, what happened so far. We presented a method to estimate the intrinsic and as well as the extrinsic parameters of a camera given 6 control points, or at least 6 control points. It's a direct solution, so we don't need to iterate that. We get our solution immediately. We don't need any initial guess for doing that. And we have kind of our nutshell handbook on how to solve that. So we have to have 4 steps: vectorizing, computing matrix M, singular value decomposition, and retrieving the individual parameters. And that's it. That's all about the DLT. That's the key things to remember. That's for the uncalibrated camera. So we use this if we don't know the calibration parameters of our camera. If we know what the calibration matrix looks like, so if we know K, then we can do that better. And this will be the topic of next week on how we actually do that. And the DLT is something which is a very central element in photogrammetry. Therefore, for the homework assignments, we'll actually ask you to compute the full DLT for an example. You can go through those individual steps and actually do those computations yourself. Kind of rather important element, and because it's the standard way, assuming that you don't have any nonlinear errors for estimating all the camera parameters from known control points. You need at least 6. You can have more, obviously. Are there any questions about the DLT so far? Key things is, what does it do? What does it do? You should be able to answer the question. What does the DLT do? What can I compute with it? In which situation can I apply it? How does the procedure work? How many points do I need? Okay? Okay, so we're making a 5-minute break now, and then we look into an alternative way for calibrating a camera. If I don't want to know 6 points in the world, if I use something kind of calibrating a camera before I take it to the field and do experiments, by basically taking a checkerboard pattern, moving a checkerboard pattern in front of a camera, taking multiple images, and then based on this checkerboard pattern, estimate the intrinsic parameters of my camera. We will rely on the technique that we have seen here, so some of the steps in there will use exactly the same steps that we have used here, but a few elements will be slightly different. Okay, so 5-minute break, and then we're going to continue